So what we're going to do here is go through a bunch of word problems using optimization to help us find minimum and maximum values. So this will probably be separated across a few videos so that you can take breaks in between, but let's just start working through some word problems. So this first one here, we want to minimize q equals 2x squared plus 3y squared, given that x plus y equals 5. So with this, something I want to think about in terms of what I want to minimize or maximize, that's what I want to end up taking the derivative of. So I'm going to want to evaluate is the derivative of q, and specifically the critical points for that. So where is q prime equal to 0? And then I'll see that those are making a minimum. Now an issue that we have is currently we have two variables. We have x and y in the same equation, and we can't have that. So that's where the second equation comes in. We know that x plus y equals 5. So what we want to do is either replace x with something in terms of y, or replace y with something in terms of x. Basically, we want to get q so that it is all in terms of a single variable. Doesn't matter which one we use, it'll get you to the same answer. So let's just say I take x plus y equals 5 and solve for y. So I have that y is equal to 5 minus x. So what I'm going to do is go to q. So I have q equals 2x squared. I'm leaving that alone, but then I'm going to have plus 3. And then where I have y squared, I'm going to substitute in 5 minus x for y. And then I'm going to start simplifying. So q equals 2x squared plus 3 times. So 5 minus x squared, that's going to expand out to a 25 minus 10x plus x squared. Then I'm going to distribute the 3 in. 75 minus 30x plus 3x squared. And then combine like terms. So q equals 5x squared minus 30x plus 75. Cool. And right now, something I could do is I could notice that this is a parabola. So this is a quadratic equation. So if I was graphing this and our value for a is a positive 5, so what that would mean is we have a parabola that's opening upwards. So just kind of using my knowledge of quadratic equations, I can get a visual for the graph. And so if it's a parabola opening upwards, that means there's this minimum value occurring. So where that minimum is going to be occurring is where our derivative is equal to 0. So this is where we go and take the derivative. So the first derivative is going to be a 10x minus 30. Set that equal to 0. And solve. So 30 equals 10x, so x is going to be equal to 3. So we have our x value, then our y value is just going to be 5 minus 3, which is 2. So to minimize q, we use x equals 3 and y equals 2 to minimize q. That rhymes very nicely. Okay, so with that, we got things in terms of a single variable, simplified, evaluated for critical values, and just keeping in mind that we are in fact finding a minimum value. All right, our next example here is more of a word problem. That was kind of a nice one that was more abstract, but now let's get to our word problem. So we have a 10-inch by 10-inch piece of cardboard. So let's go ahead and draw a picture here. So I'm going to have something that's square, and it's 10 inches by 10 inches. All right. We're going to cut out square corners. So I'm taking out 4 corners that are squares. Now, we don't know the dimensions of those squares, so I'm going to call the dimensions x by x there. So we want to note that, so if we cut out those corners, then we can fold up these side lengths to make a box. So what dimensions will yield a box of maximum value? So what we want to maximize is the volume of this box, which comes from width times length times height. So if we fold up this box, what we'll have is we have this height that'll be this corner that we're cutting out, x, will create the height of the box. But then we have these side lengths that are coming from 10, but we've cut out x and a second x. So really we have this 10 minus 2x side length of the actual box. And same thing all along the side. So for volume, what we're doing is we're taking 10 minus 2x times 10 minus 2x times x for the height. So let's go ahead and simplify that down. So 10 minus 2x times 10 minus 2x is 100 minus 20x plus 4x squared. And then we're multiplying all of that by x. I'm just going to rearrange it a little bit. So 4x cubed minus 20x squared plus 100x. All right, so we want to maximize volume. So what I want to do is evaluate the critical values of this volume equation. So I'm going to take the first derivative, which is 12x squared minus 40x plus 100. And we want to see where does that equal 0. Thinking, 1 second. Yep, something didn't feel right and I moved a little too fast. When I was foiling, so 100, and then I would have had minus 20x, so that would be f40x for that not a trinomial, the cubic. So it would be 4x cubed minus 40x squared plus 100x, which means when I take the derivative, it would be 12x squared minus 80x plus 100. Okay, so going from there, what we can do is we can use the quadratic formula. So we could factor it too. This is just kind of messy. I think it'll be easier to plug into the quadratic formula. So a equals 12, b equals negative 80, c equals 100. So x is going to be equal to negative 80 plus or minus the square root of negative 80 squared minus 4 times 12 times 100 all over 2 times 12. And with that, let's go to our calculator. So, let me get my calculator on the screen here. So we're going to have a numerator, denominator, 80. Let's start with addition, and the square root of 80 squared minus 4 times 12 times 100 all over 24. So we get a positive 5 as an answer. And then the other answer would come from if we do subtraction, which is a 1 2/3, so let's do 1.67. Now, in terms of getting two solutions, and they're both positive, which in terms of a word problem, that means they're kind of both possible. However, think about the side lengths here. If our side length is a distance of 5, so and our side lengths are 10 minus 2x, so 10 minus 2 times 5, which is 10 minus 10, that side length would turn into 0. And that doesn't make sense for us. So really, we can't have 5 coming through because that's not going to give us a maximum value. That's going to make our box basically disappear. So x equals 5 is not possible. So we're going to be using the x equals 1.67. So with that, our dimensions will have a 1.67 by, and actually let's put in units. So this will be 1.67 inches by, and then we'll have 10 minus 2 times 1.67, which is 6.66 inches by 6.66 inches. So that would be the dimensions that maximize our volume. And then in terms of the actual volume, what we do is multiply those together. There's quite a bit of rounding here. We could have included more decimal points, but close enough. So about 74.07 inches cubed would be our maximum volume. Okay, let's keep going with one more example in this video that is some more business oriented question. So we have a stereo manufacturer determines that in order to sell X units of a new stereo, the price per unit in dollars must be P of X equals 1,000 minus X. So that right there is our function for price. The manufacturer also determines that the total cost of producing X units is given by C of X equals 3,000 plus 2X. So that's our cost. So find the total revenue R of X. So as a refresher, R of X comes from taking the price times quantity. So for us, we're going to take that price function. So R of X equals that 1,000 minus X. And then we're going to multiply that by X. So R of X is going to be equal to 1,000X minus X squared. So there's our revenue function. So you just take your price function times what your variable is. Our next piece is to find the total profit. So profit comes from taking revenue minus cost. So we're going to take our revenue function, 1,000x minus x squared. I'm going to go ahead and use parentheses here and subtract in parentheses c of x, which was the 3,000 plus 2x that was given to us. And then I'm going to simplify. So this is going to be 1,000x minus x squared minus 3,000 minus 2x. And I'm just going to simplify and rearrange a bit. So let's go negative x squared. Let's see, 1,000x minus 2x, so plus 998x minus 3,000. All right, so there's our profit function. So how many units must the company produce and sell in order to maximize profit? So what we're going to do is evaluate where is our profit function equal to, where's the derivative of our profit function equal to 0? And something I can notice, again, I'm just kind of keeping this in the back of my mind, like we want to make sure we're finding a maximum. So our profit function, this negative x squared plus everything else, from the x squared I can tell it's a parabola. And then with the negative out front, that tells me it's a parabola opening downward, which that shape right there creates a maximum point. So we end up having this peak in our graph, and that's what we're going to be finding. So let's take the first derivative of our profit function. All right, so we got negative 2x plus 998. And so we're going to go 0 equals negative 2x plus 998, which means we have 2x equals 998. Divide both sides by 2, and that's going to be a 499. So in terms of our question, how many units must the company produce and sell in order to maximize profit? 499 units would be our answer there. What is the maximum profit? So what we're going to do is go to our profit function and plug in 499. So we're going to evaluate negative 499 squared plus 998 times 499 minus 3,000. And that should give us a profit of $246,001. All right, and then our last piece here is what price per unit must be charged in order to make this maximum profit. So what we're doing here is we're focusing on those 499 units still because that's what maximizes profit. But if we're evaluating the price per unit, what we're going to go back to is that price function from the beginning. So that little p of x equals, and it was 1,000 minus x, so we're going to go 1,000 minus 499, which is 501. So the price we would need to set for each unit is $501 per unit, and that would give us our maximum profit. Okay, I'm going to stop this video here, but in the next video, I'll continue on with the rest of these examples.